Hello everybody, this is Ebenezer, Assistant Professor of Physics, Alpha College of Engineering. So today I am going to teach about the carrier concentration in N-type semiconductor. So before getting into the N-type semiconductor, I just want to say about the different types of semiconductors. Semiconductors are broadly divided into intrinsic semiconductor. Intrinsic is the pure form of the semiconductor, and also extrinsic semiconductor. Extrinsic semiconductor are impure semiconductors where we add impurities for the carrier concentration. Extrinsic semiconductor are further divided into two types. One is N-type and another one is P-type. Now, N-type semiconductors are N-type semiconductors are formed by adding pentavalent impurities. Now, penta stands for 5. So, when you add a pentavalent impurity, to a pure semiconductor, germanium, which has 4 valence electrons, what will you have is so let's say the germanium has 4 valence electrons. So when you add a pentavalent impurity, the 4 out of 5 in the pentavalent impurity will get in covalent bond with the 4 valence electrons of the germanium, and you will have an extra electron which contributes to the flow of current. So since there are more electrons here in the N-type semiconductor, the majority carriers of current in N-type semiconductors are electrons, right? So let me draw the energy band diagram. So you have your valence band over here, and you have conduction band over here. So since these fifth electron, the extra electrons which contribute to the flow of current, they are called as donor electrons, and the pentavalent impurities can be also called as donor impurities. So then, since they donate their electrons to the conduction band, the donor energy band is just below the conduction band. And now you can know when temperature increases, these donor electrons now move over to the conduction band. Okay, so when these electrons in the donor region goes to the conduction band, it will create holes in the donor level. These are nothing but ionized donors. So donors are electrons, ionized donors are holes. Now at equilibrium, we know the density of electrons in the conduction band should be equal to density of ionized donors, right? So let's calculate the density of electrons in the conduction band. We already know the formula for density of electrons in the conduction band, which is N is equal to 2 into 2 pi me star kt by h square power 3 by 2 e power ef minus ec by kt. Now the density of ionized donors is given by Nd. So since they are holes, absence of electrons, the condition is 1 minus F of E. So F of is the Fermi distribution function which tells about the probability of the presence of electrons. If it is absence of electron, then we have to include 1 minus F of E. First of all, let's deal with 1 minus F of E. So 1 minus F of E, you can make it as F of ED, right? So 1 minus 1 by 1 plus exponential power ED minus EF by KT. So simple mathematics, you will get 1 plus E power ED minus EF by KT minus 1 divided by 1 plus E power ED minus EF by KT. So here 1 and minus 1 will get cancelled. Okay. So you will be having 1 by, E power ED minus EF by KT divided by 1 plus E power ED minus EF by KT. Okay. Now since these are electrons, presence of electrons, the condition is E power ED minus EF by KT should be greater than 1, right? So if it is greater than 1, then the term 1 plus E power ED minus EF in the denominator, okay, will be almost equal to, since this term is very greater than this is lesser than 1. This is lesser than 1 since this is absence of electrons. So this term will get cancelled, right? So we will have 1 in the denominator, and what you will have? 1 minus F of ED will be E power ED minus EF by KT alone, right? The denominator will be 1, right? Now let's equate both the equations. Now 2 into 2 pi me star KT by H square power 3 by 2 E power EF minus EC by KT is equal to ND into 1 power 1 minus F of D, where we found out that is ED minus EF by KT. Okay, now let's solve this. So E power EF minus EC, so that side you have, in the right hand side you had ED minus EF, so let's take it as minus ED plus EF, right, by KT, and it's equal to ND divided by 2 into 2 pi me star KT by H square power 3 by 2. Right? Now let's solve this. EF and EF is there. Okay, so this is E power 2EF. So e power 2ef, right? What did we see? ef plus ef is 2ef minus we can make it as ec plus ed by kt. Okay, and the same thing is equal to nd by 2 into 2 pi me star kt by h square power 3 by 2. Okay. Now let's take log on both sides. Taking log on both sides. So let me show the previous side. So if you take log on both sides, so left hand side we will have log into exponential will get cancelled. So only this term will be there. Okay, and right hand side log nd by 2 into 2 pi me star kt by h square power 3 by 2. So 2ef, right, minus ec plus ed, okay, divided by kt is equal to log nd by 2 into 2 pi me star kt by h square power 3 by 2. Right, let's make this kt to go over here. Okay, and then also this ec plus ed term to the right hand side. So 2ef is equal to ec plus ed. Okay, then I said we have to bring the kt term this side. So kt into log exponential nd divided by the whole 2 into 2 pi me star kt by h square power 3 by 2. So now we are going to bring this 2 over here and also over here. Okay, so let's go to the next slide. So ef is equal to ec plus ed, okay, by 2 plus kt by 2 log exponential nd by 2 into 2 pi me star kt by h square power 3 by 2. Okay, now let's substitute ef value. Okay, now what are we doing? We are finding out the carrier concentration in n-type semiconductor. So substitute this ef value, this value, in the first equation. What is the first equation? Let's look into the first equation. What is the first equation? First equation is nothing but 2 into, look at this equation, this is the first equation, 2 into 2 pi me star kt by h square power 3 by 2 into e power ef minus ec by kt. So here we have to substitute the ef value. So my screen might not be enough for writing all those things. Let me try. 2 into 2 pi me star kt by h square power 3 by 2. Okay, then e power, we have to write the whole thing, ec plus ed by 2 plus kt by 2, right, into log exponential nd by 2 into 2 pi me star kt by h square power 3 by 2, right, then minus ec, right, and the whole thing, the whole divided by kt. Okay, now let's solve this equation. So you can see here here you have EC plus ED by 2. Here EC is there. So taking LCM for this, you will get EC plus ED minus 2EC divided by 2. Right? Then EC minus 2EC will give you minus EC. Right? I repeat. Taking LCM for EC plus ED by 2 minus EC, you will get EC plus ED minus 2EC, the whole divided by 2, and then EC minus 2EC, you will get minus EC. So the equation will become, now writing the exponential part alone, since I don't have space here, so you will get ED minus EC by 2. Right? Then you will have KT by 2 log exponential, then the whole thing 2 pi me star KT by h square power 3 by 2. Right? So then divided by KT. Now I am going to bring this KT over here and also bring this KT over here. So KT and KT here will get cancelled. Okay, it will exist only here. So let's go to the next one. So E power ED minus EC divided by 2 KT. Right? So what did we have? So plus 1 by 2 log exponential ND by 2 into 2 pi me star KT by h square power 3 by 2. So in order to solve this equation, I am going to make this half to go over here, okay, also over here, and 3 by 2, 2 will become 3 by 4. Okay, now I am going to make this equation solve by this form. E power A plus B is nothing but E power A dot E power B. So let's take this one as A, okay, this whole term as B. So let's see what happens. So E power ED minus EC by 2 KT dot, right, since dot is here. So E power B, E into log, exponential into log will get cancelled. So we will have only this B term, okay, which is ND power half into 2 power half into 2 pi me star KT by h square power 3 by 4. Okay, now let's substitute this one along with this one, right? So let's look at this equation. So n is equal to 2 into 2 pi me star KT by h square power 3 by 2. Then what did you had? E power ED minus EC by 2 KT into, you had ND power half, okay, divided by, what did you had? 2 power half into, look at the previous equation, then 2m me star KT by h square power 3 by 4, right? Now in the numerator you have 2, in the denominator you have 2 per 1 by 2, so here you will get 2 power half, and then you can see here 2 pi me star KT by h square 3 by 2 in the denominator. Here you can see 2 pi me star KT by h square power 3 by 4 in the denominator. So you can cancel this and you can write it as 3 by 4. Right? Now we are going to join this 2 power half and nd power half together. So n is equal to 2 nd power half, right? Then you will have 2 pi me star kt by h square power 3 by 4, right? Then e power ed minus ec by 2 kt. Okay, last thing. So if you look at the diagram, energy band diagram, let me go to the first energy band diagram. So you can see here EC, ED is there. So we saw there exponential power ED minus EC. So EC minus ED is the energy difference. So what I'm going to take is, let me take delta, this one as delta E. Okay, I mean delta is nothing but EC minus ED. Okay, nothing but ionization energy required for an donor electron to move from the donor energy level to the conduction energy level. So the previous equation will become, this one will become minus del E, since it is ED minus EC, but del E is equal to EC minus ED. So you'll get minus del E by delta. So the equation will become n is equal to 2 nd power half 2 pi me star kt by h square power 3 by 4 e power minus del E by 2 kt. So this is the carrier concentration of electrons in n-type semiconductor. Thank you everybody.